Pluto is 100 times farther from the Sun than Earth is. At that distance, working out its temperature should be simple arithmetic. Plug in the sunlight it receives, plug in the gases in its atmosphere, and the math tells you the answer. For years, scientists did exactly that. And for years, the real measurements kept coming back roughly 30 degrees colder than the equations said they should. Nobody could explain the gap. Instruments were recalibrated. Data was rechecked. The mismatch never went away. Then, in June 2025, a team using the James Webb Space Telescope confirmed exactly what was happening. And the explanation turned out to be so strange that when it was first proposed 8 years earlier, most planetary scientists didn't believe it. Tonight, we're breaking down what Webb actually found at Pluto, the 8-year wait behind the discovery, and why scientists are now saying it changes how we think about atmospheres on cold worlds across the entire solar system. Let's rewind to where this mystery actually started. In July 2015, after a 9.5-year, 3 billion-mile journey, NASA's New Horizons spacecraft became the first and only mission ever to fly directly past Pluto. Scientists expected a small, dead, unremarkable ball of ice. What they got instead was a world with towering mountains made of solid water ice, a heart-shaped plain of frozen nitrogen roughly the size of Texas, and geology that looked disturbingly young for a body sitting billions of miles from any source of heat. Because Pluto is so far from the Sun, New Horizons couldn't slow down and settle into orbit the way missions to closer planets often do. It performed a single fast flyby, gathering as much data as possible during a brief window of closest approach before continuing outward into the Kuiper Belt, the vast region of icy bodies beyond Neptune where Pluto itself resides. And wrapped around all of it was something nobody had predicted, a thin, layered haze extending nearly 200 miles above the surface, startlingly high for an atmosphere as thin and cold as Pluto's. At first, the haze was treated mostly as a visual curiosity, a delicate blue-tinted feature that made Pluto's photographs strikingly beautiful. But when scientists ran the actual temperature numbers from New Horizons instruments, the haze became something else entirely, a genuine unsolved problem. Pluto's upper atmosphere was consistently colder than standard atmospheric models predicted, by a margin far too large to explain away as measurement noise. In 2017, a planetary scientist named Xi Zhang, then at the University of California, Santa Cruz, proposed an explanation that struck many of his colleagues as close to implausible. Every atmosphere scientists had studied up to that point, whether it was the carbon dioxide trapping heat on Venus or the methane shaping the thick clouds of Saturn's moon Titan, was primarily controlled by gas. Zhang's idea flipped that assumption on its head for Pluto specifically. What if the haze itself, made of tiny solid particles rather than gas, wasn't just floating there decoratively? What if those particles were absorbing sunlight and then releasing that energy back out as infrared radiation, acting less like atmospheric dust and more like a built-in radiator, quietly bleeding heat directly into space? If Zhang was right, it would mean solid particles, not gas, were running Pluto's entire temperature control system, something that had never been confirmed happening anywhere else in the solar system. Skepticism from other researchers was understandable. The idea cut directly against decades of standard planetary science, where gas composition, not solid particles suspended in the air, was assumed to be the primary lever controlling a planet's atmospheric temperature. The theory came with a specific, testable prediction. If this haze cooling effect was real, Pluto's haze should be faintly glowing in a very narrow band of mid-infrared wavelengths. The problem was that in 2017, no instrument sensitive enough to detect a signal that faint at that distance actually existed yet. The one that eventually could was still years away from launch. The Mid-Infrared Instrument, or MIRI, aboard the James Webb Space Telescope. So Zhang's prediction sat untested for the better part of a decade, waiting for a telescope that hadn't even left the ground. Webb finally launched on Christmas Day 2021, and starting in 2022, a research team led by planetary scientist Tanguy Bertrand at the Paris Observatory pointed Webb's instruments directly at Pluto and its large companion moon, Charon. That pairing mattered more than it might sound. Pluto and Charon orbit so close together that every earlier infrared observation of the system, going back to instruments like the Spitzer Space Telescope and the European Space Agency's Herschel Observatory in the 1990s, blended their two separate heat signatures into a single combined reading. Nobody could cleanly tell how much of any detected signal was coming from Pluto's atmosphere specifically, versus Charon's icy surface nearby. Webb's much larger mirror and far more sensitive MIRI instrument finally gave researchers the resolving power to separate the two, something Bertrand himself has described as simply impossible with any earlier generation of telescope. Working across infrared wavelengths between roughly 5 and 27 microns, the team tracked how Pluto's thermal emission changed over its roughly 6.5-day rotation. By comparing that changing signal against detailed thermophysical models of both worlds' surfaces, researchers could isolate variations in temperature, thermal, inertia, and surface composition, and crucially, separate out the specific contribution coming from Pluto's high-altitude haze rather than its icy ground. That kind of sustained, multi-rotation monitoring simply wasn't possible during New Horizons' brief 2015 flyby, which prioritized capturing detailed surface imagery during its short window of closest approach rather than long-term thermal tracking. Once they subtracted Charon's contribution and isolated Pluto's signal specifically, the result matched Zhang's 8-year-old prediction closely. Pluto's haze wasn't simply scattering sunlight around passively. It was actively glowing in the mid-infrared, radiating heat outward exactly the way Zhang's model said it should. The findings, led by Bertrand, along with Zhang and his former graduate student Linfeng Wan, were formally published in the journal Nature Astronomy on June 2, 2025. The paper's title describes it plainly: Evidence of Haze Control of Pluto's Atmospheric Heat Balance. In plain language, the haze isn't decoration. It's the mechanism running Pluto's climate. Here's what that haze is actually made of and how it forms. Ultraviolet sunlight strikes methane molecules high in Pluto's thin atmosphere, triggering a chain of chemical reactions that build increasingly complex hydrocarbon compounds called tholins. As these particles slowly drift downward through the atmosphere, they accumulate in layers, giving Pluto its faint bluish tint while simultaneously radiating heat away from above, cooling the atmosphere in a way researchers say is genuinely unique among the worlds studied so far. The discovery didn't stop at temperature either. Webb's data also showed that methane escaping from Pluto's atmosphere drifts through space and settles onto Charon, where sunlight converts it into the same reddish organic compounds responsible for the large, red-tinted region at Charon's North Pole, informally nicknamed Mordor by the New Horizons science team. In effect, Pluto is slowly reshaping the surface chemistry of its own moon, an interaction researchers describe as unique within our solar system. It's a genuinely strange relationship when you sit with it. A planet and its moon locked so closely together that one is quietly seeding chemical change on the other's surface, mile by mile, over geological time, entirely through gas escaping into the vacuum between them. The Webb observations also confirmed a second, independent prediction, this one, made by Wan in a separate 2023 study about how Charon's own brightness should shift slightly as it rotates, based on differences in its surface ice. The fact that Webb's data lined up with two separately made predictions, from two related but distinct pieces of theoretical work, gave the research team considerably more confidence that they'd found the real underlying mechanism, rather than a coincidental pattern buried in noisy data. Zhang has been careful to point out how unusual it is for a theoretical prediction to sit untested for nearly a decade, and then get confirmed this cleanly. And the implications, he says, extend well beyond Pluto itself. Saturn's moon, Titan and Neptune's moon. Triton both host broadly similar nitrogen and hydrocarbon atmospheres, meaning the same haze-driven cooling process could plausibly be shaping their climates too, giving researchers an entirely new framework for understanding atmospheric behavior on cold, hazy worlds throughout the outer solar system. There's a striking connection to Earth's own deep past hidden in this discovery as well. Before oxygen built up in Earth's atmosphere roughly 2.4 billion years ago, our planet's atmosphere was dominated by nitrogen and hydrocarbon compounds, chemically not entirely unlike what Pluto's atmosphere looks like today. Studying how haze particles regulate temperature and chemistry on Pluto right now may end up teaching researchers something genuinely useful about the chemical conditions on early Earth, long before life as we know it ever took hold. It's worth being precise about what this discovery is and what it isn't. This is real, peer-reviewed atmospheric physics, confirmed through years of careful, independently cross-checked measurement. It's not evidence of anything artificial, and it doesn't need any embellishment to be significant. What makes it remarkable on its own is that it reveals a genuinely novel, naturally occurring climate mechanism, solid particles actively regulating an entire planet's temperature and reshaping the surface of a neighboring moon in the process, something never confirmed happening anywhere else in the solar system before this research came together. Researchers are already looking ahead. They're hoping to secure additional Webb observation time to track how this haze-driven cooling system responds as Pluto continues moving along its long, elliptical 248-year orbit, since its thin atmosphere is known to expand somewhat near the Sun and thin out again as it drifts farther away. Longer-term monitoring could reveal not just a single snapshot of Pluto's climate, but how the entire system behaves across timescales far longer than any single mission could observe directly. There's also a broader question researchers are now actively exploring: whether particle-driven cooling like this could apply beyond our own solar system entirely, on cold, hydrocarbon-rich exoplanets far too distant and dim for us to study in detail yet. That connection remains genuinely speculative for now, much of it still theoretical rather than confirmed, but Pluto has given scientists something they didn't have before: real, physically confirmed proof that this kind of climate control is possible in nature, not just on paper, which gives future exoplanet research a genuine foothold rather than a purely hypothetical starting point. Nearly a decade after Zhang first proposed an idea most of his colleagues considered far-fetched, the James Webb Space Telescope didn't even exist when the prediction was made. Zhang himself has said it's genuinely uncommon in planetary science for a hypothesis to be confirmed this cleanly within less than a decade of first proposing it, and that the team felt fortunate to see it happen at all. Pluto, once dismissed by many as a small, frozen afterthought at the edge of the solar system, turned out to be running one of the most genuinely novel climate systems ever confirmed anywhere in our cosmic neighborhood. It's worth remembering, too, just how differently Pluto has been treated in public imagination compared to how seriously it's now being treated scientifically. After its 2006 reclassification from planet to dwarf planet, a decision that remains debated to this day, Pluto spent years being treated by some as a minor footnote rather than a serious, ongoing subject of study. This research pushes firmly against that framing. A world once written off as too small and too distant to matter has turned out to host a genuinely unique, self-regulating atmospheric system, one where microscopic organic particles are constantly forming, drifting downward, radiating heat into space, and quietly reshaping the surface chemistry of a neighboring moon millions of miles from the sun. If deep dives into real, carefully verified discoveries like this one are what you come here for, subscribe and turn on notifications. Because Webb is still watching Pluto, researchers are already planning follow-up observations to track how this haze-driven system changes across Pluto's long orbit. And there's clearly more to learn out there.